Good day to everyone. We are the reporter of Network Chapter 2 Network Topology. So, after reading this chapter and completing the exercises, you will be able to describe the difference between physical topology and logical topology. Sketch the physical topologies of bus, star, ring, fully connected, and hybrid networks. Explain what is meant by network hierarchy. Describe how a subnet is used to manage addresses on a network. Explain what a network access point is. Discuss the difference between a public network and a private network. So, topology concerns the structure of the connections between the computers in a network. Figure 2.1 shows three computers A, B, and C, and a network used to describe a network without specifying the nature of the connections. The network cloud may compress only the network found in a small laboratory, or it may represent an entire wide area network or WAN, such as the internet. The three computers in figure 2.1 are connected in two different ways, physically and logically. Let us examine these two types of connection. So, nara ang example. Look at the picture na lang.
Physical topology versus logical topology. Figure 2.2 show the details of the connection inside the network cloud. Four intermediate network nodes W, X, Y, and Z are responsible for relaying data between of the three machine A, B, and C. 5 connections exist between the 4 intermediate nodes. This connection may be provided through dedicated phone lines, twisted pair cable, fiber optic cable, line of the site microwave, RF, ATM, or other form of electric connection. This is the physical topology of the network. We will cover the details of each type of physical next few. The logical topology has to do with the path a packet of data takes through the network. For example, from machine A to machine C, there are 3 different paths. These paths are as follows. Number 1, link 3. 2, link 1 to link 2. Number 3, link 1 to link 4. Link 4 to link 5. Clearly, data sent on link 3 will get from machine A to machine C in the shortest time, assuming our links are identically in speed, while the third path, links 1, 4, and 5, takes the longest. Due to the nature of the network communication, we cannot guarantee that link 3 is the one that is always used. It may become too busy. Its noise level may unexpectedly increase, making it unusable, or a tree might have fallen on the cable carrying link 3. So, this is the example of topology versus logical topology. Packets of data may take different routes through the network, sometimes arriving out of the order at their destination though they were transmitted in order. They may also arrive with errors, having been corrupted somehow during transmission, or they might not even arrive at all, perhaps being dropped by a router somewhere along the way with uncertain types of network communication. It is also possible that duplicate packets of data are generated if an acknowledgement is not received by the source computer. It is the job of the network software protocols to properly resemble the packets in. Next is referring to logical connection and physical connection may seem confusing, but there will be many examples of each presented in the following chapters. For example, there are logical addresses and physical addresses at work in a network. Being familiar with the logical and physical aspect of network will go along with toward a clear understanding of the role
When a large amount of data must be sent between machines on a network, it is possible to set up a virtual circuit between the machines. A virtual circuit is a prearranged path through the network that all packets will travel for a particular session between machines. For example, for reasons based on the current state of the network, a virtual circuit is established between machines B and C through links 4 and 2. All packets exchanged between B and C will take links 4 and 2. Another type of virtual connection is called a virtual private network, or VPN. A VPN uses public network connections such as the internet or the telephone system to establish private communication by encrypting the data transmitted between the two computers of each end of the connection. Finally, special switches are available that allow virtual LANs or VLANs to be created. For example, 20 computers connected to 3 VLAN capable switches may be grouped into 2 or more VLANs with the switches configured as indicated in the table 2.1. So this is the example of grouping 20 pieces in 3 virtual LAN. So look at the picture na lang. Here you can see that the 20 pieces have been grouped into 3 VLANs. VLAN 1 contains 5 pieces, VLAN 2 contains 8, and VLAN 3 contains 7. Network traffic, including broadcast traffic from one VLAN, does not affect other VLANs. It is almost as if there are 3 physical networks of computers, even though all 20 pieces share the same physical
Next, fully connected networks. In Figure 2.3 show 4 basic types of network connection. The fully connected network, also called a mesh network in Figure 2.3, A is the most expensive to build, for each node has a link communications channel to every other node. Just adding one more node for a total of 6 nodes bring the number of links to 15. 7 fully connected nodes, Figure 21 links. In general, the number of links. So this is the example of fully connected network. In table 2.2 show the number of links for several values of n. It is easy to see that the number of links required in a fully connected network quickly becomes unmanageable. Even so, fully connected networks provide quick communication between nodes. For there is a link path between every 2 nodes in the network, even if a link goes down. The worst case path only becomes 2 links long, so fully connected networks are very reliable and somewhat secure, since many links have to fail for 2 nodes to lose contact with each other. So here the table of 2.2 number of links in a fully connected network. In fully connected network, the number of connection at each node equals the total number of nodes minus 1. So this is the example. In general, a mesh network is a collection of computers that are not connected in a bus, star, or ring topology. The term full mesh or fully connected mesh is only used when each node is connected to each other node. A partially connected network does not have as many links as a full mesh, making it less reliable.
Star networks. A figure 2.3b shows a star network. All nodes connect to a central communication hub, also called a concentrator. For small networks, only a single hub is required. For 8, 16, 32 or more connections are available on single hub. Large star networks require multiple hubs, which increase the hardware and cabling costs. On the other hand, if a node on the network fails, the hub will isolate it so that the other nodes are not affected. Entire groups of nodes machines can be isolated at a time by disconnecting their hub. This helps narrow down the source of a network problem during the troubleshooting. One characteristic of a hub is that it broadcasts data received on one port to all other ports, essentially sending copies of network from node to all other nodes on the LAN. In this way, each node on the network has an opportunity to see each packet of network data. Similar device called a switch learns where to send the data, eliminating a large majority of the broadcast traffic on the LAN. The switch also provides the star topology. Bus networks. A bus network uses a single shared common communication media that Figure 2.3c shows a single segment of a bus connection. A 10 base 2 or 10 base 5 Ethernet network uses coaxial cable as the common connection. All nodes on the common bus or cable compete with each other for position, broadcasting their data when they detect the bus is idle. If two or more nodes transmit data at the same time, all accumulation occurs, requiring each node to stop and wait before transmitting. These techniques of sharing a common bus is known as carrier sense multiple access with collision detection, or CSMA/CD, and is the basis of the Ethernet network communication system. Wiring a bus network is not too difficult. Suitable lengths of coaxial cable are daisy chained via T connectors into one long segment. Each T connector plugs into a network interface card. Each network interface card represents a node on the coaxial segment. If, for example, there are 10 nodes on the segment, then 9 lengths of coaxial cable are needed. On each end of the 9 lengths of coaxial cable, a special metal connector called a BNC connector is crimped onto the coaxial cable. The BNC connector plugs into one side of a T connector, so in the daisy chain bus, a length of coaxial cable connects one node to another on each end of the daisy chain. The T connectors only have one coaxial cable plugged into them because they are the first and last nodes on the segment to prevent signal reflections. The other side of these T connectors has special 50 OHM or terminating resistor plug into them. In summary, the 10 node bus requires 9 lengths of coaxial cable, 10 T connectors, and 250 ohm or OHM terminating resistor. The problem with the daisy chain bus connection is that bad crimps on the BNC connectors, poor connections in the T connectors, or just an improperly terminated cable segment Number 50 OHM terminating resistor can cause intermittent or excessive collisions. The source of this problem can be difficult to find. The 9 lengths of coaxial cable in our example will have 18 BNC connectors crimped onto them. Any of these crimps can cause a problem. If not done correctly, a special piece of network test equipment called a time domain reflectometer (TDR) is used to send a pulse down the coaxial cable segment and determine where the fault is by displaying a response curve for the cable. In terms of convenience, the bus network is relatively easy to set up with no significant hardware costs. No hubs are required with 185 meters of cable possible in a segment. For 10 base to Ethernet, a large number of nodes can be daisy chained together. Individual segments can be connected together to form larger network with repeaters.
Next is ring networks. The last major network topology is the ring. As figure of 2.3 show, each node in a ring is connected to exactly two other nodes. Data circulate in the ring, traveling through many intermediate nodes if necessary to get to the destination. Like the star connection, the number of links is the same as the number of nodes. The difference is that there is no central hub concentrating the nodes. Data sent between nodes will typically required paths of at least two. Hybrid network. Hybrid network. To a hybrid network combines the components of two or more network topologies, as figure 2.4 indicates. Two star networks are connected with three additional nodes via a bus. This used to be a common way to implement internet, with coax running between the classroom or laboratories and hubs in each room to form small subnetworks. Putting together a hybrid network takes carefully planning. For these are various rules that dictate how the individual components may be connected and used. For example, when connecting internet segments, a maximum of 4 repeaters may be used with 5 segments. Furthermore, if a 4 Mbps token ring network is an interface with a 10 Mbps internet network, there are performance issues that must also be taken into consideration, because any internet traffic is slowed down to 4 Mbps on the token ring side. In addition, the overall organization of the hybrid network from a logical viewpoint must be planned out as well. This will become clearer in the next section. So, this is the example of hybrid network.
So, network hierarchy. The machines networked together in figure 2.4 are not organized into a hierarchy, a layered organization. Data transmitted by any machine are broadcast through both hubs. Everyone connected to the network sees the same data and competes with everyone else for bandwidth. The same network is illustrated in figure 2.5 except for a few hardware modifications. Both hubs have been replaced by 10 Mbps switches, which act like hubs except they only forward data selectively. For example, any machine in group A can send data for any other machines in group A through the switch without the data being broadcast on the 10 Mbps backbone. The same is true for machines in Group B. Their traffic is isolated from the important 10 Mbps backbone. So, here's the example of hybrid network with hierarchy. So, look at the picture na lang. Replacing a hub with a switch leads to better performance because the switch provides dedicated bandwidth, whereas a hub provides shared bandwidth. Imagine 10 users on a 10 Mbps shared Ethernet LAN or network. In fairness, each user should have 1 Mbps or bandwidth available to them. In a 10 Mbps switch Ethernet LAN, each user has 10 Mbps of bandwidth available. Next is subnets. Each node on a TCP/IP network is assigned a unique address called an IP address. An IP address is a 32-bit number used to locate and identify nodes on the internet. For example, the IP address of one computer in a classroom LAN might be 192.203.131.137. Other computers on the same network may begin with 192.203.131 but have different numbers at the end, as in 192.203.131.7 or 192.203.131.63 and 192.203.31.440. This type of network is called a Class C subnet. A subnet is a portion of a network. For example, the Class C network 192.203.131.x may be partitioned into 4 subnets of 64 addresses, each as follows. So, number 1, 192.203.131.0 through 192.203.131.63. Number 2, 192.203.131.62 through 192.203.131.127. Number 3, 192.203.131.128 through 192.203.131.191. Number 4, 192.203.131.192 through 192.203.131.255. Subnetting is a logical, not physical activity and is accomplished using a special subnet mask such as 255.255.255.192 that is logically and with an IP address to determine its network address. The network mask is used to separate the IP address into two components, the network portion of the address and the host portion of the address. Here, in a large network such as an industrial network containing several thousand computers, subnetting plays an important role in address management when combined with the traffic management features offered by VLANs and the network hierarchy provided by switches. The network technician has a great deal of control over the operation and performances of the network.
Network access points. In the beginning of the network age, an experimental network was created by connection between 4 major data processing facilities located in Chicago, New York, San Francisco, and Washington, D.C. So this is the 4 major data processing facilities. Today, facility all across the country called network access points, NAPS, provide access to national and global network traffic. Many companies have installed their own independent communication network that connect to one or more more NAPs or even act as NAP themselves. Figure 2.6 show the RWA software national backbone a fully connected network. Although RAW software is a fictitious company, it is a representative of many national companies that have offices and therefore networks spread out over wide geographical areas. RWA software network can exist separate from the internet or can tie into an internet NAP of any one of more of 5 facilities. Companies that connect to a NAP enter into pairing agreements with each other that allowed them to Next is public network versus private networks. The two most pervasive public networks are the PSTN or Public Switch Telephone Network and broadband cable. Initially used for cable television, now used for internet access and digital voice communication as well. Because of the large number of users, access is relatively inexpensive and maintenance cost per user is small. Because access is public, some limitations are required. For example, is broadband cable. Broadband cable internet providers limit a user bandwidth to a user from using too much of the available bandwidth. Other limitations concern legal matters such as court order needed for wiretapping and in some cases that location of troubleshooting techniques. It is a fact of life that we must worry about intentional harm being done to our network. In terms of security and reliability, we must concern ourselves with what is required to partition our network, breaking it up into at least two pieces that cannot communicate with each other. Note that we do not want our network to be partitioned. So here the example. When we troubleshooting a network, knowledge of its topology, both physical and logical, is essential to understanding how the network has been partitioned so that testing and repairing can proceed smoothly. That's all, and thank you for listening, and just read it carefully, and God bless us all. Thank you.